Hello everybody and welcome back to another episode of Math with Sohn. Today we're going to be learning about pressure and doing some actual examples with it. Now there's two different things that you could be talking about with pressure. You could be talking about pressure where if I take this pen and I decide to push into my finger, it might leave an indentation. And that is because this pen is very tiny fine print point here. And I am applying not a big amount of force, but because there's such a small area, it kind of hurts. All right? Versus if I take the blunt end of the pen and I apply the same amount of pressure, that doesn't hurt very much. Okay? So that tells us that pressure is relating to the area in which you're applying a force. All right? If you have a very big area, we can multiply this out. The force that is dealt with it is pressure times area. So the force that you feel is directly proportional to the area and the pressure. So like we have all of this stuff combined in a way where you're going to feel a lot. If you have a very tiny area, it is going to apply a ton of pressure, because if you divide by a small number, you get a ton of pressure. And that pressure is what you're feeling, and that is giving you all of that force in a tiny, tiny, tiny area. Versus if you spread it out, you're less likely to go through something, which is going to be what our first example is talking about here. We have ice that is 3 inches thick. All right, and it can withstand a pressure of 14 kilopascals. 14 kilopascals is 14,000 pascals. All right, and we're not going to talk about atmospheric pressure right now. Would a large person with a mass of 80 kilograms and a singular foot area measuring 0.013 meters cubed, that should say squared, be able to walk across the lake safely? Okay. Now the first trick here is recognizing that this is a singular foot. You walk on 2 feet. However, you could maybe interpret it instead of walking in terms of standing, because when you're walking, technically 1 foot is in contact with the ground. If we draw like a stick person here, like when you're walking, this is the worst stick man ever. 1 foot is on the ground while the other one is like moving, and we're going this way. All right, so 1 foot would be holding all of your weight at one time by technicality. All right, so that means that all 80 kilograms are technically going to be on this lake. Now, if you stood still, you'd be able to split it evenly. So the force that 80 kilograms would be 80 times 10. mg is 800 newtons. All right. And we have a singular foot of 0.013. Well, we need to determine if it is going to be more than 14,000. Again, pressure is equal to force divided by area. So we have our force, 800 newtons. We have our area, 0.013. Let's see what pressure that is. All right, let's see what pressure that is. Got a calculator right here. 800 divided by 0.013 is a lot of pressure. That pressure is 61,538 pascals. Now, even if we split that up to being with 2 feet, we are still going through the lake. All right, so I would not recommend walking on this lake. All right, next part. How could you ensure that a very large person, this very same large person, could walk across the lake safely? Well, we would need to, again, instead of putting all of that pressure in a singular foot, maybe let's spread it out to being a bigger foot. Okay, so we could walk on snowshoes, so to speak. Wonder how big the snowshoes would have to be. All right, well, we're still going to have the 800, so we still have the force of 800, but what would we have to divide by area-wise in order to not go through that 14,000 Pascal threshold? Well, if we flip-flop these around, we would multiply by A and then divide by 14,000. You get 800 divided by 14,000 would equal the minimum area that we would need. 800 divided by 14,000 is a 0.057 meters squared area, which is, I don't know, if we're putting it in American standards, it's about 3 times your normal foot. All right, so it's not going to be very good for that. All right, an automobile is inflated tire to 250 kilopascals if the surface area of the tire is 1.5 meters squared, Then what force is exerted on the inside of the tire? We're going to ignore atmospheric pressure. That's another thing. So we got 250,000 kilopascals. So that's 250, not 250,000 kilo, 250,000 pascals. The surface area is 1.5. This is as simple as it gets. Pressure is equal to force divided by area. So we just have to take and plug in our area as well. 250,000 would equal force divided by 1.5. Multiply by 1.5, and you get 375,000 newtons of force. That's quite a bit overall. That's a lot of force overall. But that's okay. I mean, that's kilopascals, you know? Unless I made a mistake. 1.5 meters squared. There's a lot of area squared here. Yeah, it's just that's the overall force that the tire is experiencing, which is way more than you think. But when you narrow it down to like each individual part, it's not as bad. All right, last one for this one, I believe. We might do a little bit more. Let's see. We got a stopper syringe filled with water is compressed with a force of 20 newtons. So we got 20 newtons right here, force. As shown, calculate the pressure of water inside the syringe and the force acting on the stopper. So we got 20 newtons going up, and then here's the stopper right here at the other end. All right? So if we have 20 newtons being pushed up and the diameter of the piston is 2 centimeters, we need to first convert that into meters. That is 0.02 meters, and this would be 0.004 meters for the other one, and that is the diameter, so we technically have to cut it in half because we are going to need to do area here. Area it's force divided by area. All right, let's do the math. We have a 20 Newton force, and that 20 Newton force is going to be, for our pressure, is equal to 20 newtons divided by pi r squared for area. We have our diameter. We would need to cut that in half to get the radius, so our pressure is going to equal 20 divided by pi times radius, 0.01 squared. 20 divided by pi, I'm using 3.14 times 0.01 squared. I got an answer of 63,694, give or take, pascals. Okay? Now that's the pressure there, but notice how we narrowed it down. So when we narrow it down, this is going to increase in pressure and on the stopper because it's confining all that pressure into one little area. So this is going to have more force attached to it than originally the 20 newtons here. Okay? So when we deal with the new one, we have a new force. We have the pressure. Well, pressure times area is equal to force. Remember, because pressure is equal to force divided by area. So we have the 20 Newton force that was initiated in, but this stopper is going to get more. We have 63,694 pascals of pressure, and we have that equal to force divided by the pi r squared. The r this time is 0.004 divided by 2. So we're going to plug that in, and I'm going to multiply it. 63,694 times pi times 0.004 squared. That would equal the force, and I would expect it to be more. Let's see if it is. If it's not, then everything I've said up to this point is a lie, and I don't know what I'm talking about, and I'll have to restart the video, which would be really sad. Squared. Uh-oh. The force that this one is feeling is 3.19 newtons. Now let's think about that for a second. Why is it less? How in the world is it less? Well, again, all of this force is being pushing up into this. Let's think about this for a moment, because I just said I'd have to restart the video, and I don't really want to do that. We are 9 minutes in. All right, so we got all this force going up. Pushing into here, it is going to feel less force because it's applying it over a smaller area, all right? And that is something that will lead us into the very next problem, which is hydraulic systems. I'm not going to do all of this one here. This is going to segue us, all right? In this scenario, all right, if we have a car on this side, which is what we typically would have, we'd have something very heavy over here, something that you would typically not be able to lift. And if you apply a force on this right here, you can apply a small force for a very long duration, a long distance, and that would equate to the same amount of work that would be needed to lift something very heavy. So essentially, some tiny kid over here can push something down with a small force over a tiny little surface area, and that would be able to lift a very heavy object up on the other side. All right? And that is because the pressure is the same on both sides, and that is going to be the segue into the next video. Until next time, everybody, stay positive. We're going to explain why this force is a little opposite of what you would actually think, and then we'll learn a little more. See you then. Bye.